Today, we're going to dive into something pretty incredible: how we actually taught machines to understand language. I mean, we've gone from computers seeing words as just data to them getting the super subtle nuances of how we talk. It's a wild journey.
So let's just jump right in with a puzzle. It's a puzzle that honestly stumped computer scientists for decades. How does a computer know that the word cell can mean two completely different things? You and I, we get it instantly. But for a machine, well, that's a massive challenge.
Right? You see, the prisoner was in his cell, and you picture a jail. Then you see the cell has a membrane, and you're thinking biology. Our brains just do that. But a computer, it just sees the same four letters, C-E-L-L. Without that surrounding context, it's totally lost. It has no idea these are different concepts.
Okay, so to really get how we solve this, we have to understand the core problem. And the problem is this: computers can't read. To a machine, words are just meaningless bits of data. They process. They don't comprehend.
You know, in the early days, computers had no way of seeing that words could be related. They were just like different sequences of characters. So think about it. Table and desk, we know they're super similar. But to a computer back then, they were as different as table and rocket. Zero connection. The whole concept of meaning just wasn't there. So the first big attempt to fix this was a method called one-hot representation. Okay, picture a giant spreadsheet with like every single word in the English language. Each word gets its own unique line, and on that line, just one little box is checked off with a 1. Everything else is a 0. So every word has a unique address, which sounds good, right? But there was a massive flaw.
And yeah, this analogy just nails it. It's like a dictionary. It tells you a word exists, but it tells you absolutely nothing about how it connects to any other word. So the word king was just as far away from queen as it was from carrot. No relationship. At all.
So clearly that wasn't going to work. A totally new idea was needed. And the breakthrough came from a simple but really powerful observation about how we humans actually use language.
And here it is. This is the big idea. You shall know a word by the company it keeps. The whole theory is that words that show up in similar contexts probably have similar meanings. So if we just analyze which words hang out together, we can start to build a map of their relationships.
This one insight kicked off a whole evolution, really in 3 big stages. First, we started by just counting words. Then we got smarter and learned to predict them. And finally, we figured out how to adapt to context. So let's start at the beginning with stage 1, the count-based models.
Yeah, these early models were basically statistical brutes. I mean, they would just churn through billions of sentences, counting every single time one word appeared next to another. Then, they'd use some pretty clever math to crunch all that data down into what you could call a semantic map. A map where words with similar meanings were physically plotted closer together.
Now, counting was a great first step for sure, but it was also kind of inefficient. A bit clunky. The next real breakthrough wasn't about looking backwards and counting what already happened. It was about looking forward, teaching the machine to predict what was coming next.
And this is where the strategy really shifted. We moved from that 2-step count everything then shrink it down process to something way more elegant, a 1-step predict to learn method. So instead of just tallying up word pairs, the models were trained to play a game, basically. The game was, here's a sentence with a missing word. Guess what it is based on its neighbors.
This new era, which was really defined by models like Word2Vec, was a total game changer. Seriously, just by getting good at this prediction game, the neural network automatically learned how to create these incredibly rich, super useful word maps, we call them embeddings, and it did it way more efficiently than the old counting methods. This is what really opened the floodgates for this tech to be used in all sorts of new ways.
But even with these really sophisticated maps, there was still one critical flaw. See, on these maps, every word had only one fixed location, just one spot. And that created this problem of blended, averaged-out meanings, which, if you think about it, brings us right back to our cell problem from the beginning.
Okay, so take a simple word like mouse. How does one of these static maps handle it? Is it the little furry animal, or is it the thing you click with?
Well, here's the key. The system is forced to create just one single blended meaning for mouse. It has to find a single spot on its map that's kind of halfway between rodent and computer device. And what you end up with is a representation, a vector, that's not really accurate for either context. It's a useless compromise.
And this analogy just perfectly illustrates the solution. We had to move away from a static paper map of language
and upgrade to a dynamic, real-time GPS for word meaning.
This is exactly what modern models like Elmo and, of course, BERT do. They don't have one fixed location for the word mouse. Instead, they generate a brand new, totally unique representation for that word every single time it's used. And that representation is based entirely on the journey of the sentence it's in.
Okay, so let's tie this all together. Because this technology is not just some abstract theoretical thing. It is literally the engine inside the AI that you use every single day.
Think about it. When Google search just gets the nuance of what you're asking, or when ChatGPT can hold a really coherent conversation, or when you see language translation that is just stunningly accurate, all of that is possible because of this ability to grasp context. And it's all powered by these dynamic, contextualized embeddings.
So when you boil it all down, this whole journey's been about one thing: teaching machines to stop just processing individual words and start actually understanding conversations. We've gone from a rigid, fixed dictionary to a fluid, context-aware GPS for language.
And that leaves us with one last kind of provocative thought to chew on. As this technology keeps getting better, as its grasp of context becomes more and more human-like, it really forces us to ask a much bigger, much deeper question. What does it truly mean to understand?